relative velocities is basically a comparison of two different velocities, or it's basically looking at what's the apparent velocity, right? It might not be the true velocity, but what does it look like, or what does it feel like the velocity is? What is the velocity relative to something else, right? That's really kind of what relative velocity is. It's kind of a combination of vector addition and velocity, okay? So relative velocities are observations that are made in different reference frames and the relationships to one another. So the example I can kind of give you is that if you have two trains that are traveling towards each other at 80 kilometers per hour, let's just visualize that. Okay, you've got two trains traveling toward each other at 80 kilometers per hour. Someone standing beside the tracks would be able to visualize that those two trains are traveling at the same speed. Would you agree? Right? If you're standing on the side, you would be able to see that they're both traveling with equal speed. Would you be able to know that it's 80? Probably not, right? But you would be able to see that they're traveling at the same speed. However, if someone's standing on one of the trains, right, you've changed your point of reference. Now it looks like that train is coming at you with twice the speed, right? Because you are traveling one direction, the other train is coming at you. Can you visualize what that would look like? Right? The distance between you is closing at twice the rate. So it's going to feel like that second train is traveling twice the speed. So answer this. If I'm driving down the road 70 miles per hour and I come up on somebody that's traveling 55, what's it feel like is happening? I don't think so. Put yourself in the driver's seat. You're going 70. The person in front of you is going 55.
Oh, in front of us.
Right, in front of us. It feels like you're crawling. You know what I'm saying? You experienced that before? You're driving fast. You come up on somebody that's driving slow. It doesn't just feel like now you're going 55. It feels like you're going 15, right? It feels like you are just crawling because you had to change that speed. Does that kind of make sense? That's what I'm talking about when we talk about different frames of reference. Okay? All right. If you have velocities that are traveling in the same line, those are the ones that we just gave an example of. It's simple addition or subtraction to figure out what the relative velocity is. But if you've got relative velocities that are not in the same line, we just use vector addition to basically solve for their relative velocities. Okay, so lots of examples in this section of the chapter would be like, the plane's trying to fly north, but the wind's pushing it to the east. So what direction does it really look like it's flying, right? Or I'm trying to swim upstream, but the stream's pushing me back down and I've got to work against the current, right? Things like that. Those are the types of questions we're going to be answering. Does that kind of make sense, what we're looking at here? Right? We're trying to figure out, are we fighting with the current? Are we fighting against the current? Is the wind pushing us? Is the wind hindering us? Things like that. Okay, so here's the thing with a relative velocity. It's so important for us to draw a diagram. It's important for us to draw vectors tail to tip. It's important for us to label the resultant vector correctly because our resultant vector won't always look like what we think it does. Okay, so we're gonna go through some examples in which that's the case. Okay, so let's just dive in with some practice here. A boat needs to travel straight across the water, straight across the river. The river is flowing 1.2 meters per second west. They leave the shore with a speed of 1.85 meters per second. At what angle do they actually leave the shore, and at what speed does it appear they're traveling? So let's draw the diagram first, right? There's a lot of information happening here, but here's my boat. Here's where I need to end up, right? I need to end up straight across from where I started. Would we agree with that? Okay, it says the current is flowing west. So if I need to end up across from where I started, should I leave this direction, or this direction? Right? To the left, forward, or to the right? To the left, right? Because my current is going to push me west. Right? The current is coming from the west, right? It is flowing. Wait, which direction is west? Yep. Yep, you're right. West is the other way. My bad. I'm going to draw my diagram over here. Sorry. I confused west with east. Okay, let's try it again. Nope, yep, you're right. Okay, so let's think about this. Answer my question again. Do I need to leave left, straight, or to the right? To the right. Okay, sorry. I had west and east backwards in my head, okay? So I'm going to leave this direction. The current is going to push me to the west. so that I end up straight across from where I started. So my resultant vector here is not my hypotenuse this time, right? We've had this kind of pattern of my resultant vector always being my hypotenuse, but in this case, I'm leaving at an angle so that my current pushes me straight across from where I started. We kind of make sense about that diagram if I draw it right the first time, okay? So it says the current's flowing 1.2 meters per second. I leave the shore with the speed of 1.85. It says at what angle did I leave the shore and at what speed does it appear that I'm traveling? Okay, at what speed? So if I was watching from the shore, it might look like I'm swimming straight, right? But really I'm having to go at an angle to let myself get pushed back, okay? So we've got to figure out what are those two things. And all it is here is simple Pythagorean theorem or trig functions, right? So I could use Pythagorean theorem or I can use trig functions to solve for the side of that triangle. You can do what you choose, okay? But let's go ahead and solve for that first. Would you prefer to use Pythagorean theorem to solve for the side? Okay, so if I'm going to use Pythagorean theorem on that side, I would say a squared plus b squared equals c squared. Right? I'm going to go just like that, and I'm going to solve for the side of my triangle. It's not the hypotenuse, but one of the sides. So I got my side or my relative velocity to be 1.41 meters per second. Is that what you had or no? I'm getting a few slight nods. Okay. All right, very good. So if I was watching from the shore, it would appear that I'm swimming slower than I actually am, right? I'm having to work against the current to end up where I want to be. And so if I'm watching from the shore, it looks like I'm going slower than I actually am. Okay? Any questions with how we solved and got that 1.41? Okay, lastly, I want to find the angle at which I left the shore. This I could use any of my trig functions because I was given, I've got all three of my sides, but I'd probably use opposite and hypotenuse, so sine, right? And if I want to find the angle, I've got to use second sine or inverse of that sine to do that. So second sine of 1.2 divided by 1.85. And I get an angle of 40 degrees, 40.4. We can take one decimal there. 40.4 degrees what of what? We're always going to call this kind of our coordinate system just like normal. So north, east, south, and west. East of north. Very good. Second sine, and then I took opposite 1.20 divided by my hypotenuse. So 1.20 divided by 1.85. Okay, so these ones, the same boat now heads directly across the stream. Whoops. Oops. The same boat heads directly across the stream at 3 meters per second north with the same current. What's the apparent velocity of the boat? So now this time, it's not trying to fight against the current. It's going straight and it's letting the current push it wherever it wants to. Okay, so let's figure out what the diagram looks like here, right? I'm leaving straight north, 3 meters per second. I'm going to let the current push me west. And so my apparent velocity would be that I'm traveling at an angle there. You see what's happening? Okay, so my apparent velocity would have to be both the velocity and the angle. So we would solve both parts of that. And in this case, our resultant vector is the hypotenuse. Right, so it makes it a little bit simpler.